In this second part of the Cam-Clay model, we're going to see how to calculate elastic and plastic strains. In order to do that, we are going to base our calculation on the strain decomposition principle that tells us that we can divide elastic strains, or we can add up actually elastic strains and plastic strains in order to obtain the total strain. And the same principle is going to apply for incremental changes of strain, that we can partition those into elastic and plastic strains. So we're going to use then the Cam-Clay model in order to calculate these strains. And here's my mouse. Let me tell you what we're going to do. Basically, our objective is going to be to find out what are the proportionality coefficients that tell me what is the strain that I should get as a function of a change or an incremental change of stress. Basically, this is going to be a stiffness matrix, and we're going to have an elastic stiffness matrix, and also we're going to have a plastic stiffness matrix. So with those two, now we're going to be able to calculate that total strain, including the elastic part and the plastic part. All right, let's get started with that, and we're going to start with the elastic strains. Before writing exactly the equations for the elastic strains, let's start here with an explanation of what are the strains that we are going to be measuring. At some time we have discussed a test which is called a uniaxial strain test, or also what is known mostly in the geotechnical community as an odometer test, in which what you do is constrain a sediment within a cylinder which is very stiff, so there is no displacement to the side, and you apply a stress just on vertical direction. Usually these type of tests are done in such a way that the fluid that is within the pore space of the sediment can escape through end caps and through ports made in these end caps, so that if you do have any excess pore pressure, that one is released during the loading. And basically what you obtain with this kind of test is going to be a compaction curve. A compaction curve that is going to tell you how porosity changes as a function of the applied effective stress. And what you might expect is that as the vertical effective stress increases, the porosity is going to decrease. And more or less, this kind of plot looks like this. You start loading and porosity starts decreasing, and at some point, like somewhere over here, you might reach what is called a pre-consolidation stress. By the way, this kind of test is called also the consolidation test. And okay, that's the test, but this is the pre-consolidation stress. Once you reach that pre-consolidation stress, after that you start to see significant changes of porosity with increasing effective vertical stress. So that increasing a little bit the effective vertical stress is going to cause a more pronounced change of the porosity. And that's why this is called a pre-consolidation stress, because before this point, during loading, most of the strain is elastic. And after you reach the pre-consolidation stress, the deformation is going to be plastic. Notice that after that point, the porosity changes significantly as you increase the stress. And it may happen too that after applying that load, you may decide to unload this particular sediment. And what you're going to see in that case is that if this is the point at which you stop the loading and you do the unloading path is going to be different to the loading path, and is going to follow mostly an elastic recovery of strain. And the difference between here and there at the same stress now is going to be the irrecoverable strain done through plastic deformation. So this type of phenomenon and this type of curve can be analyzed, and this is what is mostly done, and it's very similar in a plot that links the void ratio, which is a function of porosity, and the logarithm of the effective vertical stress. And these curves are going to transform into lines. This is what most of the sediments look like. Notice, let me increase this a little bit to the left so I show that there is some curvature. So when I transform this into a logarithmic scale, this is going to look like this. This is going to be the path of loading. This is going to be my pre-consolidation stress. And this is going to be the part of the plastic loading, or what is also called the virgin compression. And again, here I have my pre-consolidation stress. Okay. And let me add here, this is the consolidation test. This same physics, we can explain it a little bit differently. Instead of doing a consolidation test, which is under a uniaxial strain condition, also called an odometric condition, we can do it under isotropic condition, in which we increase stress in all directions. And that is what we called before an isotropic compression. And the result is going to be the isotropic compression line. But this is going to be exactly the same physics and the same phenomenon. So when I do that, when I do this type of isotropic compression, then I'm going to get the isotropic compression line. And it's going to look very similar to what I have on top. And it's going to have parameters that are going to be the ones I'm going to use in my formulation. All right, so here, now I'm going to have the natural logarithm of the mean stress, P prime. I will have a loading section, pre-consolidation stress, virgin compression with plastic strains, and if I had any unloading, this is going to be the unloading. Let me try again that. All right. From here, I can get the coefficients that are going to characterize this kind of deformation. For example, from the elastic loading section, I can get the slope of this line, and it's going to be characterized by that slope kappa. Remember that this is during loading. Here, I'm going to have the pre-consolidation stress that it's P naught prime. On this section, I'm going to have a slope, which is characterized by lambda. And I'm going to assume too that during unloading, I have the same stiffness than during loading, and it's the same parameter kappa. There is something that I like that you notice in this case, and this is the fact that we are not using a linear elastic model. Now, this is a non-linear model because now I have stress with a logarithm. And because of that, the model is going to be non-linear, still elastic, but now it's non-linear. All right, let me add a few things here to complete my drawing. Notice that we have also used the convention in which the unloading path is the same as the loading, at least for the stiffness in the elastic strains, and this is going to be plastic loading. I forgot to add here that these both are elastic paths, and the equations that come out from this plot are the following. These are just equations of the line based on the natural logarithm of P prime. So this is times the natural logarithm of P prime. This is for the elastic part, and let me continue now just talking about the elastic part because those are the equations that we want to develop right now. Okay, from here, from this equation that tells me the change of pore ratio with the change of mean stress, I can also convert this into an incremental version by taking the derivative of the void ratio with respect to the change of mean stress, and this is just going to be K over P prime. Notice that derivative of the natural logarithm of x is 1 over x, so that's why I have this in here. Okay, so now with these two equations, I'm going to be able to continue my derivation of the calculation of the plastic strains. All right, let's come back a little bit to what the definition of void ratio is. If you remember, the void ratio is defined as the volume of the voids or the volume of the pores divided the volume of the solids, which is volume of the bulk part divided minus the volume of the solids. Let me check what I use here. So I use the same. I use BP. Okay, let me use the same BP for volume of the pores. Up. So this is going to be BP minus BP minus BP. All right. From here, I can obtain that also I can calculate by derivatives what is the incremental change of void ratio. And this is going to be a function of the change in the volume of the pores plus the change in the bulk volume. And based on this equation, it's just going to be math. All right, we're going to do an assumption here in order to continue with the derivation. We're going to assume that any change in the bulk volume is going to be caused by a change in the pore volume. And if you remember from pore elasticity, that would mean that the sediment is a lot softer than the grains, so that the grains do not change in volume significantly. And from a point of view of pore elasticity, that means a VO coefficient more or less equal to 1. All right, So this assumption again is valid whenever you're dealing with soft sediments. Okay, taking into account this equation, then I can write now that any change in volumetric strain is going to be equal to a change in the bulk volume. So by definition, this is actually the same thing, this equation is equal to the change in pore volume divided the change in the bulk volume. Actually here I should use the change in the bulk volume, right? But with this assumption now I can write the change in the pore volume. And by using this equation, what I'm going to be able to do, let me actually make this that explicit so I don't skip any steps here. Okay, now by using this equation, I can write what is going to be the change of void ratio based on the change of the plastic strain or the volumetric plastic strain. Remember that this P prime in terms of stresses means a mean stress, in terms of strains means a volumetric strain. All right, so with this equation now, I can go ahead and write combining what I have developed before and considering this assumption that the change in the void ratio is going to be equal to negative 1 plus the void ratio times the plastics times the volumetric strain. This is just math and comes from this volumetric relationship. So don't worry much about how specifically you get there, but believe me now that it's true, and you can also check it on your own. Okay, let me call this one equation number 2, and let me call the equation that I obtained up here equation number 1. Remember that equation number 1 just comes from this figure. Equation number 2 comes from the definition of void ratio and how that links to volumetric strain through this definition. All right, I can put 1 and 2 together and obtain the following: that the volumetric strain elastic component is going to be equal to kappa plus 1 plus the void ratio times the change in the mean stress divided the current mean stress. This is the nonlinear part. So again, all I'm doing is combining this equation with that equation. You see that we have a shared here change of void ratio, and there is the kappa and there is the 1 over E. So this is going to be the result of combining these two. And also I can write, and this I'm not showing here the derivation of this strain. Well, this is going to be the elastic component of the deviatoric strain, and this is going to be equal, and it's going to be proportional, or inversely proportional I should say, to the shear modulus G, something that we have already seen before, and it's going to depend on the changes of deviatoric stress, where here the deviatoric strain is equal to 2/3 of epsilon 1 minus epsilon 3, and this is a definition. All right, so far we have used the compaction curve. We have used just the elastic part in order to calculate what are going to be the elastic volumetric strain, and also we use the shear modulus in order to tell what is going to be the elastic deviatoric strain. Notice that here this is still linear elastic. This one is not. It's non-linear, but it is elastic. All right, so let's go ahead and do the last step. And the last step is going to be to put these equations in form of a matrix. In this case, this is going to be relatively straightforward. Let me put the volumetric strain elastic component and the deviatoric strain elastic component, those two as a vector, and here is going to be my matrix, and here is going to be my change of stress, where the change of stress is the change of the mean stress, and here I have the change of the deviatoric stress. All right, so notice that these are not related to each other. So what that means is that I still have that assumption that we have seen before, which is that the decoupling between the normal strains or volumetric strains and shear strains. Basically, here, what I'm going to have is the first coefficient is going to be this section, and it's going to be kappa 1 plus E times 1 over P prime. Well, remember, P prime is a variable, but this volumetric strain does not depend on a deviatoric stress, so this one is a 0. And the same for this one. The deviatoric strain does not depend on the mean stress, so it's also 0, and the proportionality coefficient here is 1 over 3g. And that's it. That's how we can calculate the elastic strains, of course, before yield. Let's go now into calculating the plastic strains. So section 2, plastic strains. All right, for the plastic strains, we're gonna use the flow rule that we saw before. Remember that we are dealing with it's actually called the modified Cam-Clay, the one that we're using. And this modified Cam-Clay model has a critical state line with slope m. And let me add here that this is the Q and P space. And we have a yield surface, which is an ellipse. And let me see, starting from the right, I can. Not bad, that's better ellipse than what I tried before. And we have a yield surface in which the plastic strains are going to be given by a vector which is normal to the yield surface. And I can decompose vectorially this vector into the component in the volumetric strain and the component on the deviatoric part. And this is what we're going to do. The equation for this yield surface is equal to is Q squared minus the slope of the critical state line times P prime times the pre-consolidation stress minus P prime. This is not P naught, this is P prime. All right, I'm going to write this same equation, but a little bit differently. so it's more convenient to work with, but it is the same thing. And this can be written as P prime over the pre-consolidation stress is actually going to be a dimensionless version of what I had before. And I'm going to introduce a new parameter here, eta, and we're going to see what that is in a minute. All right, so this is the equation, and here eta is going to be q divided p prime. All right, let's now go ahead and calculate the derivatives. Because we did the derivatives is how I'm going to continue and apply the flow rule. And the derivatives of this function are going to be the derivative of f star with respect to p prime is going to be the following. And same thing, but with the plus sign over here. Partial derivative of f prime with respect to q. Remember, these are our three variables. Is this times m squared, and now 2 times eta m squared plus eta squared. And finally, the variation with respect to the pre-consolidation stress is p prime divided p naught squared. Before I forget, let me tell you something about the pre-consolidation stress. The pre-consolidation stress, which is this parameter over here, it's usually known in practice and in geology as the highest stress that the rock has seen in its history. Sometimes you can have a rock at a given location at a given depth that had a lot more of effective stress in the past, and that stress was taken out by a geological process. So because the rock saw a higher stress in the past, then that means if you apply a new stress which is not as high as that stress in the past, the rock might behave more or less elastically, and it will come back to the so-called virgin compression line once you reach that pre-consolidation stress, or the largest stress that the rock has seen in its history. That's why it's called a pre-consolidation stress. All right, so this is a very important parameter then in the modified Cam-Clay model. And now that we have the derivatives, we can start applying the flow rule and we can calculate the plastic strains. All right, so let me do this. We're going to use, in this case, the associated flow rule. And for the associated flow rule, we just basically use the yield surface as our function to calculate the plastic strains. So we're going to use, in this case, F star directly. And from here, if I apply the flow rule to what I had before, I'm going to get that the plastic strain in the volumetric component is going to be equal to this times df with its partial derivative on pre prime, and for the deviatoric component, same thing, hardening parameter with the derivative with respect to q. Okay, let me now use what I learned from the isotropic compression line in order to calculate what is a change of plastic strain with a change of mean stress. Okay, so not from the flow rule, but from the isotropic consolidation line. Notice that, let me come back over here. In this region, if I have a change of the mean stress, I can predict what is going to be the change in void ratio, and also we know how to convert this to now to plastic strains through this relationship over here. So I can tell you what is going to be the increment on plastic volumetric strain on this section based on the parameter lambda and also on the parameter kappa. So from the isotropic consolidation line, I'm going to get this equation, which is going to be that the increment in plastic strain on the volumetric component is going to be equal to lambda minus k, minus kappa actually, 1 plus the void ratio times a change of the pre-consolidation stress divided the actual consolidation stress. And let me call this one equation number 4, and let me combine now what I had from the flow rule and from the yield surface. So if I call this one equation number 3, and also I take into account this derivative over here into 3 and replace it in there, what I'm going to obtain is the following. Is that, as you see, I know the derivative, I know this part because it's all of this, so the only thing that I have left here that I don't know yet is the hardening parameter. And using 3 and 4, I'm going to obtain that hardening parameter is equal to lambda minus kappa divided 1 plus the void ratio p prime m squared plus eta squared. And since now I have the hardening parameter and I have all my derivatives, I can compute now the plastic strains on the volumetric component and on the deviatoric part. Alright, so this is the last step in calculating these plastic strains. And let me go ahead and write those directly as matrices. So I also save some space. Similar to what we did before, we're going to have the volumetric component, plastic part here, and we're going to put the deviatoric component, but now the plastic part here on, as the second element of this column vector. Here I'm going to have my matrix, and here I'm going to have my input, which is going to be same as before, change of mean stress, change of deviatoric stress. And now using the hardening parameter and using the derivatives, I'm going to be able to compute these two. Okay. Notice over here that, for example, for the plastic strain, as I replace the hardening parameter and I multiply it times this other quantity, I'm going to have into my equation both changes of mean stress and changes of the deviatoric stress. So when you actually go ahead and do the math for this, you're going to find that the plastic strain in the volumetric part is going to, I missed here a coefficient, I think that should be enough. It's going to be proportional to a coefficient that depends on lambda, kappa, which is the one that we see over there, 1 plus e, p prime, and m squared and eth squared. And here I'm going to have m squared, eth squared, and now I'm going to have a component eta, actually 2 eta, in the diagonal. And what that means is that opposite to everything what we have seen before for the elastic part, now I do have that a deviatoric change of stress can cause a volumetric change or a volumetric plastic strain. So now I don't have this principle of decoupling between volumetric strain and shear anymore. Now I do see from this matrix that changes on the deviatoric stress can cause a volumetric strain. And for the deviatoric strain part is going to be similar. This matrix is also symmetric. And here I'm going to have 4 eth squared divided m squared minus eta squared. Let me change this eta. I don't like that much. So this is eta squared. And this is our plastic matrix, all of this. And now with this equation, I can calculate the plastic strains. I'm putting together the elastic part and the plastic part. Now I can calculate the full strain for this elastoplastic model. All right. So let me see if I forget anything over here. Okay, no, I don't think so. So let me continue then with the last part of this lecture. And here I'm going to give you a hint about how to implement this in a code, and to talk to the final topic that I'd like to discuss in this video. So let's come back one more time to our yield surface and with a given critical state line, where this is going to be my ellipse. Let me try one more time. Okay, that's not too bad. And remember that what we're trying to do here is to calculate plastic strains. So for example, we have seen that if we were to do a triaxial test on what is called the wet side of the yield surface, where we see strain hardening, then this is going to look something like this. Let's say that I start somewhere over here. I go with a triaxial test up to the yield surface. Up to this point, if you want to calculate epsilon q as a function of the change of q, the only thing that you have to do is to use the elastic component. All right, and this is going to be elastic because you remember that we said before that this is going to be linear elastic if you just change q. Remember, this is a triaxial test, So the slope is 1 to 3. So up to this point, the only thing you have to do is to you fix a change of the deviatoric stress and you calculate the elastic component of the deviatoric strain with this equation. Remember that here dp is not changing. Well, it's actually changing 1/3 of dq. So okay, let me correct that. Both of them are changing. But what I meant is we are only plotting here epsilon q. All right, so up to here, this is going to be elastic, right? Once you go into the plastic part, you need to explore this path. And in order to do that, what you should do in order to calculate the the plastic strains is to take small steps into doing that calculation and small increments of P prime and Q in order to utilize this matrix. Because if you just were to go from here to there, you wouldn't get the right answer. So what you have to do here is, after this point, take increments of stress small enough so that you calculate the new strain cause, including the plastic part. And this is going to be the first interval, then the second, and then so on until you get to the critical state line. And this is going to look like this, where all this section is computed with the plastic part. So the first section is elastic, the second section is going to be plastic. And again, you have to use here small increments of dq and dp in order to obtain these strains that now include the plastic part. And you will do that through that matrix. Okay. If you wanted to implement the strain softening part, that's a little bit more difficult and includes what is called a return algorithm. So that, for example, if you start somewhere over here, you go through the critical state line, also a triaxial test. Here, you not only go in one direction, but then you have to come back. And that's going to be a little bit more difficult to implement. And we're not going to see it here. But what you're going to get, it will be something like this. As we have seen before, you're going to have an elastic part, then this is going to go through a peak, and then it's going to go into a softening. And eventually go into the critical state, where here is going to be the end of the elastic part. And this is going to be strain softening. So we're not going to discuss in how to calculate those plastic strains, but I'd like to talk a little bit about the physics of what's going on here and why we have strain hardening and why we have strain softening. And I think this is a very, very cool explanation. And I borrowed this from my PhD advisor. And it is based on the following. Imagine that we have a solid which is, or a rock that is composed by strain softening material. And let's go ahead and divide this material into a grid and several grid blocks, so I can track each grid block individually. I'm going to apply stress until the material starts to fail. And remember, all of these blocks are composed by strain softening material. Let me say one more thing after I fix this. There is a small variability in the properties of the rock, and that's also natural in rocks. They are not perfectly homogeneous, but you always have some small variabilities. So one of those blocks may have a slightly bigger or slightly smaller peak stress than others. All right, so if I load this material to failure, at some point, some of these blocks is going to fail. And let's say this is the weakest grid block within that material. Because the material is strain softening, that means that as soon as it fails, the material is going to say, all right, I give up. I cannot take any more load. I'm going into the strain softening side, and I cannot take any more load. I'll take some, but not as much as I was taking before, because I've gone through my peak. And what's going to happen? The stress that this material was taking, this grid block was taking right here, now is going to be taken by the adjacent blocks. And remembering also the theory of shear strength, we have seen that fractures will tend to align onto a given angle, right? So very likely the material next to it with a higher stress, it could be either in this diagonal or in this other. And these are going to be the two next blocks, let's say, that probably we can also choose these ones, but let's say this and that are stronger than this and this one. So the one that now is going to take the load that the first one gave up to take is going to be this one and that one. But if, let's put numbers here. If 2 and 3 are taking new load and they were already close to the peak, then now they're going to be over the peak. And if they are over the peak, they are going to break too. And if they break, they will transfer the load to the adjacent grid blocks. And this is going to continue until that process of failure goes into a single trend aligned with the direction of the stress loading and the shear loading. But the important thing to capture here is that this is what is called a positive feedback mechanism, because it's like a domino. Once you break the first one, then the next ones, they are under a condition of unstable equilibrium, and this is an unstable process. So the next grid blocks are going to fail because the first failed before, and this is going to continue, and this is what is going to create a very clean fracture in this material. So strain softening material is going to tend to create, when it fails, a fracture that is very well defined, and in this case will be a fracture in this direction. That's why we see that many times when we fail a rock with unconfined conditions, we create a very nice fracture because we go through the strain softening, we go through a very well-defined peak, and we see this very well-defined failure region, which is also called a region of strain localization. And this is going to happen in the strain softening case. Let's see what is going to happen with the strain hardening and try to understand a little bit more the physics of the strain hardening problem. Okay, in strain hardening, I'm going to have a situation which is the following. Let's consider a material made of strain hardening blocks, which I'm going to divide into a grid. And similar to what I did before, I'm going to load it to failure. If I have a strain hardening material, that means that whenever some of these grid blocks go into the plastic regime, let's say this one over here, what it's going to do is it's going to get stronger. And as it gets stronger, what this material is going to do is going to have no problem in taking that stress, but not only that, is going to get stronger, and what since it doesn't have problem in taking more load, some other material next in the rock is going to go into failure. So if number one goes into failure, doesn't mean that this is going to load the adjacent or the neighbors with more load. It's just going to take it. And as it continues taking load, probably at some point, number two will show up, number three will show up, taking more load and and going into the plastic regime. And eventually, when all the grid blocks start taking more load, you could have adjacent blocks that now also start to get stronger. And number six, but since they are all able to continue taking load, the process is just going to continue, and everything is going to get stronger as a whole. And in this case, what we're going to have is opposite to what we had before. We're going to have a stable process. And what you see over here are not going to be clear shear fractures, but it's going to be something a little bit different. You could have strain localization, but this is going to be in the form of shear and compaction bands. And opposite to the previous case, this is not going to localize just into one region with a triggering point and everything aligned to it. This is going to be more or less a diffuse process and a diffuse deformation. And a material which is failed under these conditions, instead of having a clear and visible fracture, is going to have multiple fractures or strain localization regions, not really fractures, that develop strain localization, but they do not coalesce into a single strain localization feature. So this is going to be diffused deformation and plastic strain. And I have one example to share with you about this process. Just give me a sec that I find it. And I can share it with you. Okay, so this is going to be in my notes, and it's in section 4.7, where here we see an example of what we were discussing before. Failure very nicely localized with strain softening with clear fractures, and diffused failure for strain hardening and having failure more or less everywhere without a very well having a very well localized region. And there are two more things that I like to share with you. First is to tell you that these models of soft sediments lately have been very successful in modeling processes in mud rocks at the small scale and also at the geological scale. Here I have one paper that, if you're interested in this topic, I suggest that you read. And the paper deals with the deformation of mud rocks and sediments adjacent to salt bodies. And here the authors use a model very similar to the one that we have seen in order to model plastic strains adjacent to, as I was saying, to salt bodies in more or less soft sediments. And let me just scroll down, just look at a few images to see what they do. And here we have a salt body, and what they're doing is predicting stresses using this elastoplastic model. So you see there is an elastic region, a plastic region, and in this case it's very important to capture that plasticity. And with that you can predict a lot better what are the stresses in situ near some of these salt bodies. But what I want to highlight the most here is that the equations that they use are very similar to the ones that we have used in this class. And if we go to the appendix, here you see the kappa, the void ratio, the change of volumetric strain for the elastic part, for the plastic part, the yield surface, the same one as the one that we used, the slope of the critical state line, again, the same thing, and the hardening rule, it's very, very similar to what we have used in this lecture, but with different variables for the names. But essentially, it's the same model, the modified Cam-Clay. So you can use this type of model for soft sediments, but also you can use it for very well cemented rocks. And I wanted to highlight here another paper that also uses an alternative version or a branch of the modified Cam-Clay model in order to predict viscoplastic deformation in shale. And here the authors go also into deriving this particular model with very similar principles than the ones that we have used. Here you see, again, the void ratio is in there. This is the modified Cam-Clay model with a yield surface very similar to the one that we have seen before, similar equations, but now applied to shales, particularly to shales which are source rocks. So I'm going to put this the link of this paper also in the video, and here also you have the ellipses that we have seen so far that hopefully are going to help you to get started in a path in order to solve problems of elastoplasticity for petroleum and subsurface engineering.